In this module, we shall discuss maxima and minima and their various applications. First is the definition of maxima and minima. Let f be a function of n variables x1 going till xn defined over a set S in Rn space. Suppose that C is equal to C1 going till Cn belongs to set S and given a value of f that is larger than or equal to the values attained by f, all other points x equal to x going till xn of S. Suppose that C contains variables from C1 going till Cn and belongs to S and gives a value of f that is larger than or equal to the values attained by f at all other points x going from x1 till xn of S. In symbols, then we can write f of x is less than equal to f of C for all x in S. Then C is called as global maxima point for f in S and f of C is called as the maximum value. Similarly, if C going from C1 till Cn belongs to S and gives a value of f that is larger than or equal to the values attained by f at all other points x going from x1 till xn of S. In symbols, we can write f of x greater than equal to f of C for all x in S. Then C is called as global minima point for f in S and f of C is called as the minimum value. As collective names, we can use extreme points and extreme values to indicate either maxima or minima. After studying this module, you shall be able to know the concept of maxima and minima, know the various applications of maxima and minima. Let's see the necessary first order conditions for C to be a maximum or minimum point for f. For a function of n variables, vector C is equal to C1 going till Cn is called a stationary point of function x1 till xn if x is equal to C is a solution of the n equations. First derivative of fx with respect to x1 is equal to 0 going till last derivative of fx with respect to xn equal to 0. Theorem: let f be defined in a set S in Rn space and let C equal to C1 till Cn be an interior point in S at which f is differentiable. A necessary condition for C to be maximum or minimum point for f is that C is a stationary point for f, that is f dash C is equal to 0 for I going from 1 till n. Let's find out how to define a local maximum. The point C is equal to C1 going till Cn is said to be a local maximum point of f if S is fx less than equal to f of C for all x in S sufficiently close to C. More precisely, the requirement is that there exists a positive number r for which f of x is less than equal to f of C for all x in S with x minus C less than r. Here, we take a look at how to define a local minimum. Similarly, the point C going from C1 till Cn is said to be a local minimum point of f in S if f of x is greater than equal to f of C for all x in S sufficiently close to C. A stationary point C of f that is neither a local maximum nor a local minimum point is called a saddle point of f. Theorem: let f(x,y) be a function with continuous partial derivatives of the first and second order in a domain S and let x0, y0 be an interior point of that S, that is stationary point for f, where capital A is equal to double derivative of f11 x0, y0 b equal to f double derivative 1 2 x0 y0 and c double derivative of f 2 2 x0 y0. Now, if a is less than 0 and ac minus b square is greater than 0, then x0 y0 is a local maximum point. If a is greater than 0 and ac minus b square is greater than 0, then x0 y0 is a local minimum point. If ac minus b square is less than 0, then x0 y0 is a saddle point, and if ac minus b square is less than 0, then x0 y0 could be a local minimum, a local maximum, or a saddle point. Now we begin with the topic of concave functions. The function fxy is concave if its domain is convex and the line segment joining any 2 points on the graph is never above the graph. Definition of a concave function. A function f of x is equal to f x1 going till xn defined on a convex set S is concave in S if f of 1 minus lambda x0 plus lambda x is greater than equal to 1 minus lambda f x0 plus lambda f of x for all x0s, x belonging to S and all lambdas belonging to 0, 1. The function f is convex in S if minus f is concave. Theorem. Suppose that fx has continuous partial derivatives in a convex set S in Rn and let x0 be an interior point in S. Now, if f is concave, then x0 is a global maximum point of f in S if and only if x0 is a stationary point of f. If f is convex, then x0 is a global minimum point of f in S if and only if x0 is a stationary point of f. For functions of two variables, the theorem reveals whether a function is convex or concave. Let z be a function of x and y with continuous partial derivatives of first and second order defined over an open convex set S in the plane. F would be concave, implying that f double dash 1 1 is less than equal to 0, f double dash 1 1 is less than equal to 0 and is greater than or equal to 0. F is convex if and only if f double dash 1 1 is greater than equal to 0 and double derivative is greater than equal to 0 where all the inequalities should hold throughout S. Now we take a look at the sufficient conditions for strict concavity or convexity. F double dash 1 1 is less than 0 and the matrix for double derivative is strictly greater than 0. F double dash 1 1 is greater than 0 and double derivative matrix is strictly positive where all the inequalities should hold throughout S. The mentioned results have various interesting implications in optimization theory. Theorem. Sufficient conditions for global extreme points. We assume z is a function of f x y with continuous partial derivatives of the first and second order in a convex domain S and let x0 y0 be an interior point of S at which f is stationary. If for all x, y in S one has double derivative of 1 1 less than equal to 0 and f double dash 2 2 less than equal to 0 with the given inequality greater than equal to 0, then x0, y0 is a maximum point for fxy in S. If for all x, y in S one has double derivative of 1 1 less than equal to 0 and f double dash 22 less than equal to 0 with the given inequality greater than equal to 0, then x0 comma y0 is a minimum point for fxy in S. Now let us begin with the topic of quasi-concave and quasi-convex functions. Let f of x be a function defined over a convex set S in Rn space. For each real number a, we define the set Pa by x belonging to S for f of x greater than equal to a, then P of A is a subset of S that is called an upper level set for f. Quasi-concave. The function f defined over a convex set S belonging to Rn space is quasi-concave if the upper level set Pa is a convex for each number a. Quasi-convex. We say that f is quasi-convex if minus f is quasi-concave. So, if f is quasi-convex, if and only if the lower level set P of A is convex for each number a. If f of x is concave, then f of x is quasi-concave. If f of x is convex, then f of x is quasi-convex. Theorem. Let f be a function of n variables defined over a convex set S in Rn space. If f is quasi-concave, if and only if, for all x belonging to S and all lambdas belonging to 0, 1, we have f of x greater than equal to f of x0, implying the inequality. Strictly quasi-concave. A function f of x is strictly quasi-concave if f of x is greater than equal to f of x0, where x is not equal to x of 0, and lambda lies between 0 and 1, implying f of 1 minus lambda x plus lambda x to the power 0 is strictly greater than f of x0. There are various economic applications of maxima and minima. To name a few, we have revenue maximization, output maximization, cost minimization, utility maximization, and profit maximization. Now, we study every economic application in detail. To begin with, we have revenue maximization. Let total revenue function be equal to P dot X, where P is price and X is the quantity. Total revenue will be maximum at level of output where dTr by dx is equal to 0 or mr equal to 0 and double derivative of tr with respect to x is less than 0. The first order condition implies that dTr by dx is equal to p plus x dp by dx is equal to 0 or p by x into dx by dp is equal to minus 1, implying elasticity equal to 1. The maxima of total revenue occurs where elasticity of demand is unity. Let us understand the economic applications now with some examples. To start with, we look at an example involving the first economic application, that is revenue maximization. Consider a wholesaler of pencils who charges rupees 24 per dozen on order of 50 dozen or less. For order in excess of 50 dozen, the price is reduced by 20 paise per dozen in excess of 50 dozen. We have to find the size of the order which maximizes his total revenue. Now let's take a look at the solution to this problem. Let x be the number of dozens in an order. When x is less than equal to 50, total revenue is 24 into x. When x is greater than 50, the price charged per dozen is given by P is equal to 24 minus 0.2 into x comma minus 50. This is equal to 34 minus 0.2x. Thus, total revenue P dot x becomes 34x minus 0.2x square. We note that total revenue will have a maxima only when x is greater than 50, because when x is less than equal to 50, TR is a straight line and therefore has no maxima. For maximum TR, we have dTR by dx equal to 34 minus 0.4x equal to 0, or x equal to 84 dozens. Since the double derivative is equal to minus 4 and is less than 0, the second order condition is also satisfied. Then we begin with the application involving maximization of output. Assuming that labor is the only variable factor, we can write the production function of a firm as x is equal to f of L, where x denotes total product of labor, which will be denoted as TP. The average product of labor is AP and is equal to TP upon L. The marginal product of labor is MPL and is equal to dx upon dl equal to F dash L. The necessary condition for maximization output is dTP upon dl is equal to dx upon dl is equal to MPL is equal to 0. Often, we are interested in finding the level of employment of labor at which its average product is maximum. For this, we have dAPL upon dl is equal to 0, which gives us the condition that MPL is equal to APL. Thus, the marginal product and average product of a factor are equal at the maxima of the latter. Again, we take up an example to establish the application of output maximization. The short-run production function of a manufacturer is given as x is equal to 11L plus 16L square minus L cube. First, find the average product function APL, the marginal product function MPL, and show that MPL is equal to APL, where APL is maximum. Second, find the value of labor for which output is maximum. Let's take a look at the solution. First, APL is equal to x upon L equal to 11 plus 16L minus L square, and MPL is equal to dx upon dl is equal to 11 plus 32L plus L square. We have dAPL upon dl is equal to 0, which gives us APL being maximum at L equal to 8. Since the double derivative is negative equal to minus 2, the second order condition is satisfied. The maximum APL is 75, and further MPL is equal to 75. Hence APL and MPL are equal when APL is maximum. For the second option of maximum output, we have dx upon dl equal to 11 plus 32L minus 3L square equal to 0, or 11 minus L into 1 plus 3L equal to 0, which gives L equal to 11. The other value of L being negative is dropped. Since the double derivative is equal to minus 34 and is less than 0, the second order condition for maxima is satisfied. Another important application is the cost minimization exercise. If total cost is a function of x, then we can define AC or average cost as f of x upon x and marginal cost MC as f dash x. Very often we are interested in finding the level of output that gives the minimum AC. For minima of AC, we have dAC upon dx is equal to 0, which implies that MC is equal to AC. Hence, marginal cost is equal to average cost at the minima of the latter. Let's study a related example of minimization of cost. The cost of fuel consumed per hour in running a train is proportional to the square of its speed, and it costs rupees 3200 per hour at a speed of 40 kilometers per hour. What is the most economical speed if the fixed charges are 12,800 per hour? Let's take a look at the solution. Let F be the cost of fuel and X be the speed of train per hour. We are given that F is directly related to X square, or F is equal to K times X square, where K is a constant of proportionality. When X is equal to 40, F is given by 3200. Therefore, K becomes 2. Thus, we can write F is equal to 2x square as the cost of fuel per hour of running the train when its speed is x km per hour. Now, the total cost of running the train when its speed is x km per hour is Tc equal to 12,800 plus 2x square. The average cost becomes 12,800 upon x plus 2x. The most economical speed will be that value of x which minimizes AC. So AC upon dx is 0 for a minima, which gives x equal to 80 kilometers per hour, and second order condition provides second derivative of AC with respect to x as x equal to 80, which is positive. The second order condition for minima is hence satisfied. Let u equal to a function of x, where utility function of a consumer defines u as utility and x as a level of consumption of commodity. The utility is maximum at a value of x such that du upon dx is equal to 0 and double derivative of u with respect to x is less than 0. Now, let's take a look at an example of utility maximization. The utility function of a consumer for two goods is u equal to x dot y, price of x being rupees 10 per unit and that of y being rupees 15 per unit. If the consumer has only rupees 90 to spend on the two goods, determine his optimal purchases. The budget constraint can be written as 10x plus 15y is equal to 90. Solving this equation for y, we get u is equal to 90x minus 10x upon 15, and substituting this value in the utility function, we get u equal to 90x minus 10x square upon 15. We want to find x such that u becomes maximum. So, du upon dx is 0 with x equal to 4.5. Further, y is defined equal to 3. Since the double derivative of u with respect to x is less than 0, the second order condition for maxima is satisfied. Now we move towards the last economic application, which is profit maximization. Profit is the difference between total revenue and total cost of a producer for a firm. Now, we know that the total revenue as well as the total cost are often expressed as functions of level of output, X. If we write TR is equal to RX and TC is equal to CX, then profit can be written as pi X is equal to RX minus CX. We want to find that value of X where profit pi becomes maximum. The conditions for maxima or pi x are: first order, pi dash x is equal to r dash x minus c dash x equal to 0, or mrx is equal to mcx. Let xe satisfy the equation. Then we can write first derivative of revenue function for xe is less than first derivative of cost function of xe, where XCE is termed as the profit maximizing or the equilibrium output. Note that the first order condition is also termed as the equilibrium condition. The second order condition. In order that the profit pi is maximum and xe, we should have double derivative of pi less than 0. This condition implies that double derivative of revenue function is less than double derivative of cost function for xc, or mr-xc is less than mc-xc. That is, the slope of marginal revenue function must be less than the slope of marginal cost function at the equilibrium. Let us now summarize what we have learned in this module. First, if f is a function of n variables x1 going till xn defined over a set S in Rn space, and f of x is less than equal to f of c for all x in S, then C is called as global maxima point for f in S and f of c is called as the maximum value. Similarly, if f of x is greater than equal to f of c for all x in S, then C is called as global minima point and f of c is called as the minimum value. If f is a function defined in set S for Rn space and C goes from C1 till Cn is an interior point in S at which f is differentiable, a necessary condition for C to be a minima or a maxima for f is that C must be a stationary point for f. That is, f dash c must be 0, I going from 1 till n. The point C, C1 going till Cn is said to be a local maxima point for S if f of x is less than equal to f of c for all x's in S sufficiently close to C. Similarly, the point C is equal to C1 going till Cn is said to be a local minima point of f in C if f of x is greater than equal to f of c for all x in S sufficiently close to C. A function f of x is equal to f x1, x2 going till xn defined over a convex set S is said to be concave in S if f 1 minus lambda x to the power 0 plus lambda x is greater than equal to 1 minus lambda f x0 plus lambda f of x. For all x to the power 0, x belonging to S and all lambda belonging to space 0, 1. Quasi-concave, the function f defined over a convex set S belonging to R to the power n is quasi-concave if the upper level set P of A is equal to x belonging to S, f of x greater than equal to A is convex for each number A. Quasi-convex, we say that f is quasi-convex if minus f is quasi-concave. So, if f is quasi-convex, if and only if the lower level set P of A is equal to x belonging to S, f of x less than equal to A is convex for each number A. There are various economic applications of optimization theory like the revenue maximization, profit maximization, cost minimization, etc.